Very good morning to you all. So in today's class we are going to look for the design of the equivalent circuit of a transformer. So basically the equivalent circuit of a transformer is designed from the imperfections. The design of the equivalent circuit of a transformer is related to the imperfections in a practical transformer. Imperfections in a practical transformer. In a practical transformer, you will see that you have core losses. In a practical transformer, you will see you have core losses that are represented by your eddy current and hysteresis losses. And the previous class, what we studied, this hysteresis and eddy current losses is reduced by laminating the core and using a particular type of grading of the transformer. So again, in today's class also, we are going to see how these gradings and how this okay. So in today's class we are going to see what type of losses are there. Like ideally the winding which I told you in the previous class, the transformer is consisting of a copper winding which is not purely inductive in nature, so there is some component of resistance involved, and this component of resistance results into losses called as copper losses. So the number one imperfection in a practical transformer would be your copper loss. So in order to copper loss, that is also the resistive I square R loss. So how do you model these losses? Basically what happens is that these resistive heating losses in the primary and secondary winding of the transformer, and they are proportional to the square of the current. So it can be seen that when you have to model a transformer, we can model an equivalent circuit of a transformer by representing these copper losses as resistive losses in the primary and secondary winding of the transformer core. So they can be simply modeled by placing a resistor Rp in the primary circuit of the transformer and a resistor Rs in the secondary circuit of the transformer. So we can simply model this like this. I place a resistor Rp. This is my resistor Rp in my primary circuit. One more resistor I will put in the secondary circuit. One resistor Rs I will put in the secondary circuit. So this is accounting for my copper loss. Now, is there any other kind of loss? So what are my copper losses? These are my resistive heating loss of windings. So this is represented by this. So if I will now the second point here is that we have to clearly notice is that now we mentioned about the copper losses, and what about the core? So core is also having certain amount of losses. These core losses are represented by the eddy current and the hysteresis losses. So eddy current losses are basically the resistive heating losses in core of the transformer, and they are proportional to the square of the voltage applied to the transformer. Similarly, hysteresis losses are associated with basically what rearrangement of the magnetic domains in the core during each half cycle, as explained in the previous lecture also. So one thing was about this eddy current and hysteresis losses, and so we can say these together form core losses. Core losses, you will get I eddy, this is I eddy plus hysteresis IH, we can write I hysteresis. So these together form your core losses. So these two core losses, and the number third is your leakage flux, as we already discussed the leakage flux. So leakage flux is that flux which is not linking with both the windings, whereas the mutual flux, that is due to the mutual induction, it links with both the windings. So this leakage flux escapes through the core and pass through only one of the transformer windings and are leakage fluxes. Okay, now these escaped flux, so this escaped flux which is called leakage flux produces a self inductance, produces self inductance in primary and secondary of the coil. So one thing was this: these inductance are producing this self inductance primary and secondary of coil. So one important thing here is that, let's suppose my voltage, my ELP primary side voltage is number of turns by flux d phi by dt. So as far as my flux is concerned, flux is what? Flux is just equivalent to current is what? Voltage by R. So if you write V is equal to I by R, here you see, so your I is equal to V into V by I is equal to R. So your I is equal to, if you have to write, IR is equal to V, or your I is equal to V by R. Okay, so V is MMF, that is represented by this, and R is reluctance, and your 1 by reluctance is nothing but as permeance. So 1 by reluctance is permeance, or in other terms I can write phi LP is my permeance into my MMF. So permeance into my MMF is my flux. So from these equations we can clearly see, I am going to rub this. So I came to one conclusion: my permeance into where it went. Okay, so I came to one particular conclusion: my permeance into your reluctance, my flux was given by permeance into your reluctance, permeance into your MMF, and MMF is nothing but ampere turns, NP into IP. So this is my permeance, so I can write my flux as flux, this is my leakage flux, my permeance NP IP. Okay, similarly on the secondary side I can write permeance NS IS. So basically this is my flux. I'll write down flux is equal to my permeance flux is equal to permeance into my MMF. So that I'm representing over here. So this is my flux is equal to permeance into MMF, that I am representing here. Flux is equal to my permeance into MMF. So now I have these equations. What I can do is the elementary equation of the inductance, which I had written as my E is equal to N d phi by dt, or ELP. So I can write my flux is equal to see, the pen is also not okay. So my flux is equal to my voltage is equal to E is equal to N d phi P by dt. So d phi P by dt, so N is equal to d phi P by dt. So here you can substitute, instead of d phi P by dt you can write this from this is, if this is equation 1, 2 and 3, from 4 you substitute in 2, and you will end up with this equation would be ELP would reflect your NP, and now you are substituting that d by dt instead of phi p. What you will write? 2. You will write permeance NP IP. So permeance NP IP. So this is my equation 5. So I am going to rub these here. So let this equation 5 be here. So now what I am going to do is that I have to write my equation. So I can get my equation easily. I can write from this equation 5, my ELP is equal to NP square permeance dP dip by dt. So here you see this is the same equation. Similarly for ELS side you can write NS square rho dis by dt. So here this term You also know that ELP is what? ELP is LP dip by dt. dip by dt. So the LP term here is represented by, LP term is nothing but, LP term you can represent it in terms of NP square into permeance. So your LP would be NP square into permeance. Rest is same, na? NP square into permeance is LP. Similarly, LS would be NS square into permeance, and rest would be same. So two things you noticed. The number one thing which we have noticed is that, okay, the number one thing which we have noticed right now is we are getting these equations. So one thing was the resistance that was put, the primary and secondary resistance due to the winding. Now the due to the leakage flux there is self inductance. You can see self inductance is both in the primary and the secondary side. So you can account from this, you can account for the modeling of your part. So you can write your transformer model in terms of your resistance in the primary Rp, self inductance Rp, Lp, and now on the secondary side you can write Rs, Ls. So till here we have arrived for the equivalent circuit. Now we have left with the core loss component. So leakage flux we accounted for, copper losses we accounted for. Now there is one more imperfection, that is core loss. Now how can the core excitation effects be modeled? How can core loss be modeled? Core loss be modeled. So these core loss be modeled. How can it be modeled? It can be modeled by, see what happens is that core, when you are sending the core and you are giving the supply, because there is an excitation current, that excitation current excites the transformer. Whenever in big stations you are rigging up or installing a transformer for first time, some of you might be some of your relatives might be working in electrical power development department, or are very convenient or having knowledge of this particular field. So there is some charging of a transformer, it takes place initially. So this basically is to establish that magnetizing current. So this excitation of the magnetizing current, how it can be modeled is that the magnetization current is the current proportional to the voltage applied to the core. So this magnetizing current is current proportional to the core, and but it is lagging 90 degrees, but it is lagging 90 degrees to the applied voltage, applied voltage. So in the first class only I have told you that if your voltage is this and your current is lagging the voltage, so lagging element is represented by, lagging current element is represented by your inductance, or you can say you can represent this by your reactance. Okay, reactance. And your leading, if you have a XL, you can write XL. And if you are having a leading element, for example V, that is represented by your capacitive reactance. So this XC, this VI, this is for lagging and this is for leading. So leading is represented by your XC. And now one more thing is there. So it with the element, the core would not be purely inductive or capacitive in nature. So there is some element of resistance involved. So the core loss current, that is your IH plus E, the core loss current is a current proportional to the voltage applied to the core, that is in phase with the applied voltage. So it can be modeled by a resistance connected across the primary voltage source. So remember, these both are non-linear in nature, and your inductance XM and resistance RC, we can best approximate it to the core effects. So how can, now we are with all these constraints here, now we have to develop the final equivalent circuit. Now we saw that your core is placed in between. So how do we represent this? We came to know, okay, one element of the core can be represented by reactive element. Another element of the core can be represented as the what do you say, as a resistive element. So core is in between your primary and secondary winding, and primary and secondary winding are on one side of the core, and another side of the core you have secondary winding. One side another one side of the core you have primary winding is there, core is there, and your secondary winding is there. You can say like it's a sandwich. You have bread on top, jam, another bread. So bread on one side is your, what you can say is that primary winding, another side bread you have secondary side, in between the jam you have core. So core you can represent by your combination of your reactance and your resistance. So here you can see that core you can represent here by a combination of your reactance and resistance. So your core here you can represent like this. So you are done. This gives your GC. You can write GC 1 by RC, or you can straight away write RC also, no problem. And if you are writing XM, okay, you can write BM, that is 1 by XM. Like this also you can write straight away XM also you can write, but I'll show you why I have taken these things for elaboration. So this is your transformer. Basically this is your primary side, this is your VP. Okay, this is the primary side voltage, you are giving it to some socket. Okay, phase and neutral you are giving him socket. This is your primary side, this is your primary side current.